temperature, what will happen to average energy? Average energy per particle. Okay. I think he took total average energy. Am I right? Capital lever is total average energy. Okay. Speaker. So now, roughly near what temperature does E changes from its low to its high temperature limiting values? Okay. Speaker. Roughly. Okay. That's what he's asking. Okay. Use the result of A, make the qualitative plot of heat capacity. Okay, what is heat capacity? That's a derivative of average energy. Okay, figure as a function of temperature. Then do the explicit calculation and compare. Am I right? Verify that your expression exhibits the qualitative feature of A and B. Okay, figure. So let me start like this. Okay. Fine. This is my energy E1, energy E2, single particle energy. Okay, figure. As the temperature tends to 0, what will happen? Did you say n particle? He said n particle. Okay, figure. I mean, all n particles will be here. Okay, it's nearly 0. Am I right? As temperature tends to 0. Okay, he said qualitative plot. Okay, figure. As temperature tends to infinity, what would happen? So I think I better to draw here only. Okay, as temperature 0, it will happen. Okay, figure. As temperature tends to infinity, as t tends to infinity, what will happen? Fine. E1, E2. Okay, what will happen? N1 nearly equal to n by 2, n2 nearly equal to n by 2. Okay, we have already seen this one. So here total average energy that's equal to n into E1. Can I select this? Here total average energy that's equal to n into n by 2 E1, n by 2 E2. Okay, n by 2 E1 plus n by 2 E2. Fine, figure. Or I can write it as n into uh, n into E1 plus E2 by 2. Am I right? At t tends to infinity, this will be the energy. Qualitative plot. Okay, he said qualitative plot. Okay, average energy as a function of temperature. Okay, figure. Average energy as a function of temperature. Okay, when you have low temperature, what is the energy? N into E1. Can I select this? Figure. At low temperature, this is your energy. Okay, at high temperature, that energy goes to n by 2 E1 plus E2. Fine. N by 2 E1 plus E2. I'll just mark them. Then I will draw roughly. Okay, speaker. N by 2 E1 plus E2. Okay, speaker. Fine. Speaker. That means at low temperature, that energy will tend to this value. High temperature, energy will tend to this value. Draw a qualitative plot. Are you getting my point? Speaker. Can I select this? Roughly. And later you evaluate it, using your canonical distribution, okay, and then try to plot it using GeoGebra. How does this look? Okay, it may be quite complex, am I right? It contains numerator, denominator, and all, but you still try to what do you call plot it, okay, using GeoGebra, okay, whether it looks in the similar nature of something, okay. Now what he is saying is, okay, what he is asking, approximately at what temperature, okay, what is that? Roughly near what temperature does E bar change from low to its high temperature limiting value? That means that is this one, am I right? I mean, that's our point where our concavity, convexity changes. Can I tell you? It was concave upward, it became concave downward. You need second derivative actually. To point out this one, you need second derivative, isn't it? How do you locate? First derivative is some value here, isn't it? Second derivative will be 0. It will be concave upward to concave point of inflection. We say like this, am I right? So concave upward to concave downward, okay? You have to go for second derivative, okay? Now he's asking approximately at what temperature it changes, okay? That I don't have any, because he's again expecting this one qualitatively, am I right? He's expecting this one qualitatively. Any idea? Not by I mean, to take derivative, you need actual calculation, expression, and all, am I right? Pick up. I'll just mention directly. I don't know. I mean, how we can predict this particular temperature. Okay, that temperature is such a way that if you multiply Kb to that the temperature, that will be E2 minus E1 energy difference. Energy difference. When Kbt is equal to energy difference, this will appear. In someone, you take second derivative equal to 0 and find that point later, okay? Because not now. Fine? That's what I remember. That T naught is such a way that, that T naught is equal to, E2 minus E1 by Kv. It may be quite lengthy to prove, You need to take second derivative, you have to equal to 0, you have to solve for temperature. But I'm not getting how to explain this one qualitatively, not using the expression, Because it looks like, when your KBT, when your thermal energy, is this much, when your thermal energy is equal to energy gap, what you call, it made some transition from lower to higher or something, Pick up. No, we don't have any equation here. Am I right? He asked everything qualitatively. We don't. Electron to one state, another state, like that. Similar. It happens similar, but it's not that sharp like photon absorption. Okay. When you give exact energy. No, yeah. I mean, I'm saying it is a slow, what you call, excitation of particles. Okay. Because by absorbing thermal energy, it's not like when you make your KBT is equal to this value, all will go jump up. It's not like that. Okay, pick up. It's a slow change actually. Are you getting my point? Can you see here? And it's not like population inversion will happen. Am I right? Pick up. I mean, so when you go to very high temperature, pick up. So n by 2 will happen. Okay, it's not like your optical phenomena. Okay, but it appears so. Okay, it appears when your KBT is equal to this energy gap. Okay, pick up. Now again, wait a second. Let us. You get this point. What do you do with it one? Only that short and say we'll give n by 2 p2 minus 0. So minus y2 minus 0. Okay, you took the middle point of this. So then it's directly proportional. Okay, it is linear like that you are saying. That's a good idea. Am I right? If it is linear, what is this midpoint formula? You have to add divided by 2. That's the midpoint formula. So n by 2 E1 plus n by 2 E2. No, you have to add and divide by 2. That's the midpoint formula. No, I think he is expecting something else. Okay, speak up. Okay, if it is linear, what he's saying is temperature proportional to energy, am I right? In the linear region, you can exploit that one to write some proportionality, but that's also not E1 minus E2. Isn't it? Midpoint formula, right? It's not E1 minus E2. Minus. All length minus this length. Okay. Wait. What is the midpoint formula? It just write whatever I wrote, but it won't give E2 minus E1. I'm saying, as I remember, this is E2 minus E1. Okay. So check that out. Okay. Check that out. You think over it. Okay. So running out of time. So now next thing is, okay, pick up. Again, make the qualitative plot of, okay, pick up. What is that? Heat capacity with respect to temperature. Is that okay? Pick up. This is average energy as a function of temperature. Now make the qualitative plot of heat capacity as a function of temperature. Hmm? CV as a function of temperature. What is CV? CV is just dou E bar by dou T. You have this curve, you take its derivative. How slope changes? Isn't it? Hmm? How slope changes? This is your T naught, okay? Where it changed from concave upward to concave downward. Okay, pick up. Here slope is zero. Here slope is zero. Okay, look at here. Your specific heat, if it is your T naught, it looks like this. Don't make it symmetric. Somehow make it asymmetric. Okay, you draw like that. Okay, isn't it? And at this point, I mean, your second derivative is zero, right? Second derivative of energy is zero. It means derivative of specific heat is zero at that point. Okay, at that point, specific heat at R. Look at here. Slope is zero. Slope is slowly increasing. Slope is having highest value. Then again, slope started decreasing to zero. What is this one? This is nothing but slope of this curve. CV is nothing but slope of this curve. Derivative of this curve. Hmm. What you are saying? Derivative is nothing but slope of the tangent. Huh. That's what I have applied here. Is that okay? Pick up. Hmm? CV is nothing but slope to this curve. Okay, slope of the tangent to this curve. Okay, slope is zero. Zero slowly increasing, having maximum value at this point of inflection. Okay, again started decreasing to zero. Hmm? Heat capacity will be like this. Okay, again at T naught. Okay, which is equal to, okay, E2 minus E1 by kb. At that value, your specific heat have its maximum value. Hmm. No. That is beta derivative. While writing beta derivative, we wrote minus 1 by kb t square dou by dou beta of average energy. Okay, original definition was this one, dou E bar by dou T. This one, since average energy, our habit was to write in terms of beta, we converted as a beta derivative. But original was this one only, okay, at constant volume, okay? Hmm? Fine. So, I mean, it's a temperature derivative, okay? Because here I have drawn with respect to temperature, am I right? This is nothing but slope of this one, okay? This is what he is expecting in part A and B of the problem, okay? Draw the qualitative plot of average energy as a function of temperature, heat capacity as a function of. If you draw this one, this is the slope, okay? Slope to this one, okay? Fine, pick up. Now, I mean, this was a question, okay, in some exam, okay? Now, while drawing this qualitative plot of E bar, okay, you just need this idea, am I right? What is the energy at high temperature? What is the energy at low temperature? That you can write without, what you call, working anything, isn't it? Pick up. Without working, you can write these things, isn't it? That's what we have practiced. Hmm? Speak up. Low temperature, high temperature. Okay. Speak up. And using that one, you can just draw one smooth curve. Okay. That's it. Okay. Speak up. I think in the exam they have asked. I don't know. Maybe in one exam this one, other exam this one. Okay. Speak up. Heat capacity. Okay. For two level system. Two level system. Can I say like this? Any two level system, we should follow the same nature. What do you say? isn't it? Now, in part C of the problem, okay, what you do? In part C of the problem, now you find Z is equal.
Sir, is there any question about the CFT of the CV plot?
No. I don't think it will be symmetric.
Okay.
Have I drawn symmetric? You make it somehow asymmetric. Fine.
Okay.
Pick up. And the T naught, if you multiply by KB, that will be a gap between those two energies somehow. Okay. Pick up. Now,